Imagine writing a novel once, then having it instantly readable in any language, on any device, without rewriting a single word. That is the promise Java made decades ago. Write once, run anywhere. You compile your code, and that exact same compiled file runs on Windows, Linux, macOS, even embedded systems, without modification. It sounds like magic, doesn't it? But how does a single .class file, which is not native machine code, execute identically across such wildly different hardware and operating systems? How does it avoid the platform dependency nightmare that still plagues languages like C or C++? Today, we are going to pull back the curtain on the three core components that make this possible: the JVM, the JRE, and the JDK. By the end of this, you will clearly distinguish the roles of the Java virtual machine, the Java Runtime Environment, and the Java Development Kit. You will understand precisely how Java bytecode enables that cross-platform execution. We will identify the critical internal components of the JVM, like the just-in-time compiler and garbage collection, and understand their runtime benefits. And you will know exactly when and how to use tools like javac, Java, and the modern jlink utility. Let us start with write once, run anywhere, or WORA. Think of your Java source code, the .java files you write, as a detailed blueprint for a house. This blueprint is human readable, but a construction crew cannot build directly from it. They need a universal set of instructions. That is where the Java compiler, javac, comes in. It takes your blueprint, say myprogram.java, and translates it into an intermediate, universal instruction set called bytecode. This bytecode is stored in .class files. It is not machine code for your Intel or ARM CPU. It is instructions for a hypothetical, abstract machine. This is the first crucial step. Now, this bytecode, this .class file, is truly platform independent. It is like a standard instruction manual that any skilled builder, regardless of their native language, can understand. The magic happens because each operating system and hardware architecture has its own specialized builder, the Java Virtual Machine, or JVM. The JVM is the heart of Java's portability. It is a software implementation of that abstract machine. When you run a Java application, the JVM for your specific operating system and architecture loads your .class files, verifies their structural integrity to prevent malicious code, and then executes the bytecode. It is the universal translator, taking those abstract instructions and turning them into native operations your CPU understands. This portability does come with a trade-off: startup time. The JVM has to perform class loading, verification, and interpretation before your application reaches its peak performance. This is why Java applications historically felt a bit slow to start. However, after this initial warm-up, the JVM's just-in-time compiler kicks in, and that is where Java truly shines. The JVM is not just a bytecode interpreter. It is a sophisticated runtime environment. Inside, you will find several critical components. First, there is the class loader, responsible for loading your application's classes and the Java standard library classes into memory. Then, the runtime data areas, which include the heap for objects and the stack for method calls and local variables. But the real powerhouse is the execution engine. This is where your bytecode actually runs. It contains an interpreter, which executes bytecode instruction by instruction. More importantly, it houses the just-in-time, or JIT, compiler. The JIT observes your running code, identifies hotspots, methods that are frequently executed, and compiles those specific bytecode sequences into highly optimized native machine code on the fly. This runtime profiling and compilation is something static compilers cannot do. The JIT, for example, might see that a certain branch in your code is almost always taken, and it can optimize for that specific path, even de-optimizing and recompiling if the usage pattern changes. This is why, after warm-up, JIT-compiled Java code can often rival or even surpass the performance of ahead-of-time compiled languages. Another crucial component within the execution engine is the garbage collector, or GC. This is Java's automatic memory management system. Instead of you manually allocating and deallocating memory, like with malloc and free in C, the GC automatically reclaims memory occupied by objects that are no longer referenced by your application. This dramatically reduces memory leaks and simplifies development, though understanding its behavior is key to writing performant Java. Now that you understand the JVM, the Java Runtime Environment, or JRE, is going to make perfect sense. Think of the JVM as the engine of a car. It is powerful, but it cannot drive itself. It needs a chassis, wheels, seats, and a fuel tank to be a functional vehicle. The JRE is exactly that, the JVM bundled with everything needed to run a Java application. Specifically, the JRE includes the JVM plus the standard class libraries. These are the thousands of pre-written classes that provide fundamental functionality. Things like java.lang for core language features, java.util for data structures, java.io for input/output operations, and so on. It also includes configuration files and support files. Historically, you could download a standalone JRE, but since Java 11, Oracle and Open JDK distributions no longer provide a separate JRE package. The expectation is that you will create a custom runtime image using jlink from the JDK. Finally, we have the Java Development Kit, or JDK. If the JRE is a complete car, the JDK is the entire garage, complete with the car, all the tools to build and repair it, and even a manual. The JDK contains the JRE, plus all the development tools you need to write, compile, debug, and package Java applications. This includes the javac compiler we discussed earlier, the jar tool for archiving and packaging your code, javadoc for generating API documentation, JDB for debugging, and various diagnostic tools like JCMD or JStack. When you install any modern Java distribution today, you are installing a JDK. It is the complete package for Java developers. Let me show you how these tools work together. I am going to write a simple Java program. This code declares a class myProgram with a main method, which is the entry point for any Java application. Inside, it declares an integer variable named value and assigns it the integer 42. Then, it prints a string literal concatenated with that value to the console. To compile this, I use the javac command, which is part of the JDK. I type javac myprogram.java. If there are no syntax errors, this command produces no output, but it creates a myprogram.class file in the same directory. This is your bytecode. Now, to run it, I use the java command, also part of the JDK, which invokes the JVM. I type java myprogram. Notice I do not include the .class extension. The JVM loads and executes the bytecode. When you run this, you get exactly this on screen. The answer is 42. This simple flow demonstrates the core compile then run process enabled by the JDK and JVM. Here is where it gets interesting for production deployments. Shipping a full JDK, which can be hundreds of megabytes, into a production container or server is often overkill. You only need the parts necessary to run your application. This is where the jlink utility, introduced in Java 9, becomes incredibly powerful. Jlink allows you to create a custom runtime image. You specify exactly which Java modules your application requires. For example, java.base for core functionality, java.sql if you are using databases, or java.desktop if you have a GUI. Jlink then bundles only those modules, along with a JVM, into a minimal, self-contained runtime. This effectively creates a tailored JRE, drastically reducing the deployment size. For example, if your application only uses basic I/O and collections, you might use a jlink command like this. Jlink --add -modules java.base, java.logging --output my-app-runtime. This command creates a directory named my-app-runtime containing a JVM and only the java.base and java.logging modules. The resulting image can be tens of megabytes, a fraction of a full JDK, making it ideal for microservices and containerized environments. A common mistake I see people make, especially when they are new to Java, is thinking that javac produces native machine code directly. It does not. It produces bytecode. Another one is shipping that entire JDK into a Docker container for a production application. You are going to run into this. Remember, the JDK is for development. For production, you want a lean runtime, which jlink helps you build. So, what have you mastered today? You now understand the distinct roles of the JVM, JRE, and JDK. You know how Java bytecode enables the write once, run anywhere promise by providing a platform-neutral intermediate representation. And you can explain the critical internal components of the JVM, like the JIT compiler and garbage collection, and how they contribute to Java's performance and robustness. You are now equipped to make informed decisions about your Java development and deployment environments. Next time, we're going to dive deeper into Java's execution model, specifically exploring bytecode and JIT compilation in much greater detail.